Okay, 6 o'clock, and let me see how many guys showed up. There are 37, quite a lot. I hope everyone else will join in. So I had a question that says, oh, am I not sharing anything? Why? Stop share. Share screen. Share. Do you guys see my this Canvas homepage?
Yes.
Yes.
Okay. To answer your question, where can you see this thing? I hope there is this Zoom page, cloud recording. I have published it, so it should be available to you. Can you check?
Oh, you have it. Yeah. Thank you so much. Yeah.
Yeah, please explore the Canvas. That's quite a lot resource for you. Since we are on this page, like front page, I want you to pay attention to this header, right? So if you visit the homepage, it basically gives you the recent announcement. I hope you guys are paying attention to that. What I'm planning each Wednesday after the class, I will give an announcement which basically talks about what is the topics for the next week upcoming that you need to review, and if there are activities for the next week. So make sure you watch these videos, or at least go through this. You're aware of this page. You don't ignore that. So I hope everyone on the same page on this. So each Wednesday after the class, I'm planning to put a new announcement, which is for the next week, whatever task and course and activities you need to do. So as far as this thing, we had to do this lecture 2, and I hope you guys have reviewed the videos before coming to this class. We'll be focusing some part of this part, computer organizations, today. Basically what I'm planning to start from where I ended. So these class discussions you can treat it as a separate one, apart from the activities that you need to do yourself by watching, like for example, lecture 2. This is the lecture materials, and if you go to the module 2, module 1, there are lecture 2 videos that you need to watch and complete them. And then if I'm sure you'll have questions, then you need to go and put it in this QA section. I see there are 2 questions, one from Carter and one from Isita. Thank you for that. I will come back to these questions, okay, after I finish the discussion, what we started from last day. Question? No? Okay. Let's see. Okay, now I want to share the Jamboard of the class. How do I do it? New share. Okay. All right. Do you see my Jamboards? Okay, at least I got one confirmation in chat. You want to see that? Okay. Yeah. So this was like last day where we stopped. Basically, we started discussing about different component in a processor, and now and what are their role. Okay, that's what we started to discuss. In this diagram, I basically little bit formalized that one. All these lines and everything, these electrical line connections, etc. I just formalized, made it look nice. And basically, now today, what I'm trying to do is to explain how a program is executed in this specific in this system, in this computing system. For that, what I'll do, I will take a sample program. Okay, just very simple, high level. Let's start with a high level. Let's say I have a program like integer A10 and integer B20. Then I have integer C equals A plus B. Right? So that's my program. So basically, at the end of the day, this program is supposed to calculate 20 plus 10 equals 30 and put it in a variable C, right? So how this simple task works in a computing system, that's our quest for today. So first of all, this high level program, computing system doesn't know anything about this. Okay, it doesn't know anything about this. And what it does, basically, one thing, it does two things with this high level program. Through some transformation, translation, etc., which is not important how it does in the system, but we'll learn it. We'll learn it throughout this course about how it does it. But today, let's focus what happens. Basically, what happens, first of all, this variable, high-level variable A, B, C that we have they are basically nothing but a storage space in the memory. Okay, storage space in the memory. So that is the one thing. Actually, I'm trying to open up my Jamboard on my Surface so that I can draw. And this guy is installing something. Okay, just hold on. Okay. Oh, it is coming up. Just hold on. Okay. This page. I know I want to go. Hello. Anyway, okay, let's see. Now, these variables A, B, C, they are basically a part and storage of the memory. Let's assume A is at address 0. Means this storage space is storing variable A. Okay. Similarly, let's assume B is at 1 and C is at 2. Okay. So we my system is actually giving me trouble. Okay, so this one is B, this address is for C. So this high-level program, through some translation and transformation, it stores the value A at 10 here, and then 20, integer B equals 20 here, and C is initialized with 0, let's say. Okay, that is the initial state where when you start the program. And this part, C equals A plus B, is somewhat translated by compiler and assembler, etc. It's broken down into smaller steps. Okay, so it broken down like this. Let me write. Okay. R0 equals, I'll explain what is R0 is in a minute, equal to mem of 0, which is A, R1 equals mem of 1, and R2, oh, well, that's fine. And then R3 equals R0 plus R1, then mem 2 equals R3. Now let me explain what happened in this translation. So this R is denoting here, is denoting the register file's address 0. Okay, R0, register file, register number 0. This is register files, register number 1, and this is register file, register number 3. So what is going on in this program, just to execute one simple step of C equals A plus B, what system need to do, read from the memory address 0, store it into register 0, then read from memory address 1, store the value to the register 1, and then retrieve the value from the R0, retrieve the value from the R1, add them, store it back into register 3, and then write the memory address 2 with the value of the R3. So it's broken down into 4 steps. Now, let's say these steps, basic steps, are converted into machine codes, and it's being stored as a machine code from address. Let's say this one starting from 1, this one starting from, let's say, 1000 memory address, and this machine code is at 1001, this machine code as 1002, and this machine code as 1003. So they're part of, let's say this part is like, this part of the memory is used to store them, like 1001, 100, sorry, 100, 1001, 1002, and 1003. They're there. So at the beginning, what this controller does, it first of all, it knows where to begin. So it knows it needs to begin from 1 0 0 0. So at the very first step, which we call instruction fetch, IF. At this stage, processor issues an address 1000 and then issues an 1 to the read signal and 0 to the write signal. This means to the memory as if someone is asking from read from address 1000. And what is the stored value in the 1000? The machine code representation of this instruction. So it gets that instruction. Well, let's not go into detail what the machine code format at this point. We'll deal with that in successive classes. But let's say somehow that instruction, some value got back, we don't know what value, some value got back from the memory to the controller, and controller basically stores that instruction somewhat in a storage we call a instruction register, some mem0, etc., etc. So it stores that instruction in the instruction register. Now from that point, it goes into next step called instruction decode. It also associated with something called a register fetch. We'll see that. So at this point, processor wants to decodes this instruction stored in this instruction register and try to determine what is the next course of action. Okay, so that is the instruction decode phase. And then it realized that, hey, I need to access a memory. For that, I need to produce or generate some memory address. Okay, so that address generation is done at some phase called the EXE or execution phase. So let's put the note at that point, memory address is computed, that which memory I need to access. So it determined it need to access from memory 0. So it goes into the next phase called memory access. So at this point, what it does, it issues an address 0 and it already has the issues also at a read signal and write signal to 0. So now memory knows that it need to read from the address 0. So it sends that data, that value 10, back to the processor. Okay, back to the processor. So that value 10 comes into the processor. Let's say processor keeps it in some intermediate register called SEC or accumulator. You'll see later like there is nothing accumulator in the modern processor, but for our understanding, let's stick to that. Okay, let's say that value came here and it's being stored inside this controller, the temporary register 10. Now, the very next step, what it does is called a write back, WB. So write back stage, what it knows from the instruction that it need to write back the data read from the memory into the register 0. So what happens at that point? Processor issues 0 to the address write, okay, and a data write as a 10, value 10, so which is coming from here to there, address write to 5 and data to the data write, and sets the read and write signal accordingly, read to 0, write to 1. So at this point, what this register file now understand, hey, I am getting an address of 0, value of 10 to be written, and this is my command to write that value into that register. So what it will do, it will basically write 10 into the register file or register 0. So far, any question?
What does IF stand for again?
Instruction fetch.
Thank you.
Okay.
Also,
All right.
what is the
Yes.
IR in the controller?
IR is the instruction register.
Okay, thank you.
All right. Now the processor from the write back stage goes to instruction fetch again. So this is instruction. Now what happens at this point? This program counter is incremented by 1001, and that address now is issued as a read operation for the memory. So at that point, the memory knows that, hey, I need to read from this address 1001, which is a machine code equivalent, some representation in the memory it stores. It basically sends that value back into the processor. And that instruction simply being written over here or stored over here, like R1 equals that, whatever that instruction is written over here. And from there, now it moves to instruction fetch to instruction decode. Now again, this processor knows, hey, I need to read from the memory 1 and store it into register 1. So what happens? In the execution phase, it compute the memory address and then issues the address 1 over here, and the read signal stay as it is. Then at that point, and then the memory step, this memory knows, okay, I need to read from the address 1. So it reads the value of 20 and returns back to the controller. And that value, let's say it is being stored over this temporary register inside the controller as a 20. Now at the write back stage, what happens? Controller basically sends an address of 1 with a data value of 20 being coming from here, okay, from the accumulator to here. So and the write signal, read signal to 0, write to 1. So register file knows it needs to write value 20 into the register 1. So it basically does it. Now processor goes into the instruction fetch again. So what happens in that at that point? It basically updates the program counter to 1002, and that address being presented to the memory. Don't know what is coming up. Oops. And memory to read 1, write 0. So memory knows at that point it need to read from this location 1002, which has the machine code for this instruction, R3 equals R0 plus R1. So it sends back that instruction back to that machine code to the controller. Controller store it in here, and then in the instruction decode phase, the controller goes into the instruction decode step, and then it understands that now it need to fetch value from R0, register 0, fetch value from register 1, add them up, and store the result back to R3. So now some interesting thing happens inside the processor, okay? Just watch out. So at the same point here, it is not only instruction decode, but register fetch. So during this controller is understanding it need to fetch these registers, is also start fetching them, register 0 and 1. What happens at this point, at the same phase, so this is, let me just write it down, register fetch happens here. So it basically, let me just erase them. So at this point, it issues 0 onto address of R1, 1 into address of R2, ADRW and data W, these two doesn't matter because we are not performing any write operation. It can be anything. And read to 1, write to 0. So at this moment now, this phase, register file also knows that it need to send reads from this registered 0 and 1 and sends it back to the controller. Okay, so at the end of this phase, what it does, it will return back those values to the controller, 10 and 20. Okay, now controller goes into the exe phase, from ID phase to exe phase. At this point, what happens, it does not need to do address calculation, but it needs to do really the plus operation, right? We need to do the addition. So at this point, at this state exe, what the controller does is send the first operand as 10, second operand as 20. These two values coming from here to there, right? And 20 from here to there. So it is basically redirecting those values onto the ALU and setting up the ALU operation code for representing a plus. Remember, there is no character or any encoding, something like that. It is always a value. So ALU knows, okay, maybe value 10 is addition. And value, if a value comes in like 2, it is subtraction in the OPRN bus. So it doesn't matter what encoded it does, but it sends a operation signal code for addition. What ALU will do now, it basically sends back result 30. Okay. Now, processor goes into the mem state from here to the memory state. So this instruction does not involve any memory access, right? So it does not do anything. It just don't do anything, sit idle, and then it transitions into the write back. So at the write back point, what happens now? It issues the address 3 to the right position in data as 30, which is coming from ALU back to the registers. Okay, coming from ALU back to the registers, and simply change the control signal values, setting read to 0, write to 1. And as a result, 30 will be stored in register 3. Okay, register 3. So that's end of that instruction. So we are done with instruction R3 equals R0 plus R1. Question so far?
Yeah, I had a question.
Sure.
So when there's no number written over a line, is there no signal being sent, or is there like a blank signal being sent?
Come again, like from where?
So for instance, in one of the steps, there was no signal being sent for like a address write and data write, because there's no data being written. And those are blank. So does that mean nothing is being sent, or like a 0 signal is being sent?
It's in hardware, it is usually 0, and unless it is harmful. Usually it is 0. Okay. So there is nothing a null signal. There is some concept called electrical isolation or high Z state, but that's kind of little bit complicated. So let's assume it is 0 if it is nothing is sent.
Okay, thank you very much.
No problem.
I had a question.
Yes.
Why was register 2 skipped over?
It's just an example.
Oh, okay.
Let's say it was used for some other purpose in the software program. When high-level program being translated, that register being used already, let's say. Okay, so that's just an example. Okay, now on to the very last step. We need to write back the result from R3, which is 30, into the memory 2, which belongs to the variable C in the high-level program, right? So we do this now, okay? Now instruction fetch again, instruction fetch. So this guy goes to the instruction fetch. Same thing happens. It increases the program counter by 1, so it becomes like 1003, and this address is sent 1003 over there 1003, and a read signal, and then memory knows that it needs to send back the machine code stored in that location 1003. It sends back that XXX, okay, and it's stored in the instruction register. Now this controller goes into the instruction decode and register fetch stage, and there it knows that, hey, I need to fetch the value from register 3. So what happens now, it basically, let me just erase them. It basically now issue an address 3, maybe here. The others doesn't matter, and set value to 1 on a read and write signal to 0. So register file knows that it needs to read back from, let's say, like as I told earlier, let's say something is 0 also. It's nothing is sent means 0 is sent. So what will happen, that register file at the end of this register fetch state, it will return on the data R1 line as the value 30, and on the data R2 line a value of 10, because let's say R2 was set to an register 0. So what will happen, the controller at this point use this value only, because it knows that it is trying to fetch only one single register. So it will actually discard this value, absolutely discard the other value. So it will pick up 30, and then it will it will again do the memory address calculation because some memory has to be written back. So it calculates the memory address, calculate memory address, and it comes up with an address 2. Then it goes, or address, yeah, address 2. And then it goes into the memory state. Now at this point, it basically issues an address of 2 with a data 30 and write as 1, read as 0. So at that point, memory knows that it needs to write the value 30 onto the address 2. So it will basically update this space as 30. Okay. And then it goes into the write back. In this instruction, there is nothing to be written back into the register. It will simply skip and go to the next instruction fetch. So that's the story or lifetime of one instruction execution. Okay, it basically took me like more than half an hour to explain, and it goes blazing fast in a computing system. But all these smaller steps actually happens in a processor at that level, that each instruction goes through the 5 cycle of instruction fetch, instruction decode, execution, memory, and write back. And in the execution fetch, this is mostly involved the ALU for some arithmetic operation calculation. Instruction fetch and memory is involved with the mem. Instruction decode register fetch is mostly to do with the registered file reading, and write back stage is related to the registered file writing. Question?
Can you repeat which step involves the ALU?
EXE, execution. So anything involves calculation or arithmetic operation, it means it's ALU. Is that okay?
That's perfect. Thank you.
Okay. Now let me extend another concept to you. Okay, so this one, you see that there are several tasks involved. Like it's sometimes memory has to read something. Sometimes your controller has to store something and control back and do some register file operation. This guy needs to complete some task. ALU need to complete some task. So how to synchronize this work, right? To synchronize the work, there is this concept of this clock comes in. Okay, clock system comes in. Clock. So we have clock, right? It's very simple concept. That let's say you and me are 2 involved parties here, okay? And during the exam, I hand you over some exam paper and say the exam duration is 2.5 hours, right? So what does the expectation from each other? I give you, let's say at time 6 o'clock in the evening, hand over the exam paper, and expectation is that you will complete the exam by 8:30, right? 2.5 hours after 6 o'clock. So we are synchronizing each other tasks with respect to the clock time, right? Is the same concept goes in here in the computing system. It is basically supplies some time references to each of the system. and subsystem. It can be in the ALU too. Okay, so each of these guys has a port. A port is kind of an electrical connection between components to send some data out or have some data in. That's we call in electrical term as a port, nothing big. So there is some electrical connection to connect clock signal to each of these components. And what this clock signal does, it does not, unlike us, we are actually synchronized with some clock measurement like 6:30 p.m., 7:30 p.m., etc., like human being. Computer system doesn't do that. It doesn't even know what is 6:30 p.m. means. So how it works, basically, this system generates a train of logical 0 and 1 continuously. So we are just depicting as a picture, like this is logical 0, this is logical 1, this is logical 0, this is logical 1, this is 0, this is 1, this is 0, etc. And only constraint is this, the time period, that is when it was transitioning from 0 to 1 and again transitioning from 0 to 1, this whole cycle is constant time. This whole cycle is constant time, predefined, okay? And then these subsystems are synchronized with respect to how many clock ticks. So basically, let's say these are called ticks, 1 tick, 2 tick, 3 ticks, or how many clock cycles. Maybe there is an arrangement between the controller and the ALU that when at certain point it issues the operation code and operand, let's say at this point, T1, controller expect that ALU will be done by the next clock tick, T2. Maybe that's an arrangement. Or it can be an arrangement between two hardwares, but it is fixed upfront that, oh, why am I just erasing that? T2, T3, okay. Maybe at this point, controller issues OP1, OP2, and OPRN. And at this point, always at this point, that is after 2 clock cycle, after 2 clock cycle, ALU will return result. That can be another arrangement. But whatever is the arrangement, it is predefined. It is predefined for a simplistic system, by the way. And everyone knows when a task is given, like a task to the memory is given, hey, read from this location, everyone knows how long it will take or how many clock cycle it will take in that terms, okay? Not like a absolute timing sense, like 6 p.m., 7 p.m., etc., but it is in terms of how many clock ticks it will need to complete its task. And that is how they are synchronized, and that is where the clock system's importance is. Question? Okay, let's take then 5-minute break, and we'll be back after 5 minutes, like 6:50 maybe. Okay, 6:50. Let us be back. I have one question saying that did you take attendance today? Pop quizzes, little pop quiz. Actually, no, I don't take attendance like that. Remember, you all guys are registered viewer. So I generate a report at the end of the session that who has logged in, how long you have been watching. So yeah, if someone thinks that you just log in once and just go out, I will know, okay, how much, how long you participated in our register. So that's the beauty of registration in the Zoom, and we don't need to do an extra exercise. However, let me do a little bit polling about our preparedness. Let's see who has done their work. Where is the poll? Yeah. There. Okay. Let's take a minute. Okay. We have about 46 participants. Just, you can do it anonymously. Please do that. Okay, so yeah, there are 43 out of 46, maybe 3 more. Couple of seconds, we'll close the poll. Okay, let's take the statistics. I'm sharing the result with you guys. So about 36% of the class watched all of the videos that's supposed to be done by today. Thank you very much. For others, please pay attention. If you start falling behind, it is not an easy course to catch up. Please do so. Same goes with the lectures, 51%. That's better. I have read the lecture notes. Thank you very much. Other 50%, please make sure you do that next time. Queries, about 9% has made some queries. I don't have any question, 42%. Again, like, that's worrisome. If you don't have questions, then it's not achieving what we want to do here. Okay, so our main goal in this class is to raise many questions. Okay, if you don't have question, that means that something is missing there in your understanding. Because I know as a course, CS47 is not a complete course. It will leave many unanswered question to you, which will probably be closed in 147, computer architecture study. So this course is basically to open up the questions and get them answered in next sequel of this course is 147. So I would expect many questions from you. Okay, please review the materials critically, and I'm sure many parts would raise more questions than it's actually answering about the system. Okay, saying that, let me get back to the today's topics and if there is any question asked over the canvas.
I have a question
Yes.
about the Zoom registration. I didn't register for today's date. I just clicked on the previous date and it let me join.
I believe once you registered, you can join in. That's what the setting is.
Oh, okay.
Yeah, so maybe I'll see, like, send me an email. I'll watch out
Mhm.
if you are actually coming in that registered list or not. I believe you will.
Okay. Okay. Thank you.
Unless you are registered, one cannot attend this Zoom session.
All right.
All right. So let's see. I saw the two questions. One from Carter, other from Ishita. Let me share that. This one, share. Okay. One question. Hey, am I sharing? Are you guys can see?
It's black. Can't see anything.
Okay. Stop sharing. I don't know what is happening. As soon as I actually drag something from one monitor to the other monitor, it is going blank. Okay. All right. So let me pick up Ishita's question first, simply because it's an easier to answer than this one, Carter's question. Maybe it will take some time. So in a nutshell, Ishita, okay, let me first read the question loud so that everyone on the same page. The clock high time, TH, and clock low time used to be 50% of the each time period, clock T. Now, why are duty cycles of modern computer clock systems are less than 50%? So this is something to do with the power consumption at the electrical level. So less is the high part, less is the power consumption. Okay, that's the simplest nutshell explanation of the whole thing. So that's why designs are made like a pulse designs and stuff like that. But main target is to reduce the power consumption by the processor. And that's one factor is the duty cycle. And if we reduce the duty cycle, it tends to reduce the power in a very simplistic sense. Okay, Ishita, is that?
Yes.
Okay, now Carter, difference between read and write cycle of the memory system versus the read and write cycle of the register file. Okay, that's a good question. Let me share my slides with you and see how it differentiate. Okay, where is my sharing? New share. New share. I want to share this slides. This one. Okay. All right. So we in this flow, in this reading, we started with memory system, right? And we said that, well, memory has something like a software interface equivalent, like there is a read-write signal, there is an index value, and there is a bidirectional data for in and out. That's the memory system. And then we talked about the how the memories read and write works in terms of the timing diagram we try to explain in that video, lecture video. And there we saw that, okay, this is a storage. I have a read-write control signal. And I have a reset signal which resets the content within the memory. So let's say it is resetted everything to 0. And then in one cycle between T2 and T3, there is a read signal comes up as a 1 and write signal to 0. That means it's a command for read operation for the memory, which is like, if we just look at the software code, it's basically equivalent to that phenomena, what I'm describing. And then what happens at the beginning of this first cycle, second cycle, third cycle, this data, this memory will spit out the data onto the data bus. Okay, so that data is coming up in the data line, and processor is consuming, let's say, within a clock cycle. Then the write processor issues the write signal as is setting the read signal to 0, write signal to 1, setting up an address where to write, and setting up the data. So now at this point between T4 and T5, this time point, data is actually incoming from outside towards the memory. So it is incoming and memory will be writing it. So based on this model, we will derive the register file model. Okay, register file model. So let's first look at the difference. Okay, the difference which basically catch our eye. Okay, so look at this. There is a bidirectional data of 32 bars, right? That means physically there are 32 lines, right? Electrical lines connected to the memory, whereas a register file has a different separate data in and separate data out. Like we have like total 64 of electrical connection onto this electronic system for the register file. That is the first difference, which is differentiating structurally from the memory interface diagram and the register file diagram. So on the register file, it's a memory device, but it has separate data input and data output. One may question, why is that? This is the reason is this memory is a chip which goes on a motherboard. Okay, it is not a part of the processor. That means like more of the electrical wires need to be connected to this physical chip, physical component. It will be complicated on the motherboard, and you cannot make motherboard smaller. So that's why we wanted to have little bit complex route of defining an bidirectional data port of 32-bit, eliminating 32 more wires to route through the motherboard. So that's the simplification from the real world perspective that we wanted to do it. Now what happened to the register file? It is part of the processor. Means it is actually implemented on a piece of silicon where we have abundance of space compared to the motherboard. Of course, it's a relative term, abundant and stuff like that. But compared to the motherboard, the amount of space we are getting to route different electrical connection is much less on the motherboard compared to the silicon, which is basically a processor implemented in the silicon, on the silicon, and register file is part of the processor. There we have a scope to actually simplify our life from the operation perspective by separating out the data in and data out. So as soon as we actually separate the data in and data out, two ports separately, then we can actually do not need a wait time for a back-to-back read-write operation. Look at this picture where we made a read request at T2. It took a cycle to complete that request, and then memory spit out the data onto the data bus. Now, during that time, of course, a processor cannot initiate a write operation because write operation need to send the data in. But here we have only one data line. So we must wait till we consume the data, means processor consumes the data, and then only it can raise a read or successive write request. But as soon as we split this data in-out type data into one data in and another data out, as in register file, we no longer have that constraint. So as a result, what happens, I can issue a read operation at T2, and its data will come out on the data out part. I think one label is missing right here. Should be a data in. I don't know. Okay, anyway, I'll fix it later. So it will, as a read operation, this address, this operation, T2 cycle initiated, that data, read data comes out at the T3 on the cycle, but that does not preventing processors to issue a write operation at the same cycle, initiating at T3, where it's simply issuing a different address and presenting the data to be written on the data input. Okay, so that's the main difference between the operation of the memory versus the register file. Is that okay, Carter?
Yes, I explained it very well. Thank
Makes
you.
sense? So now, while we are here, let's just look at what else has been changed from here. So this model and this model, the change has been made. We split out the data into two parts. Now we want to do is more. Basically, we added one more output port for the second register reading with another set of addresses, okay? Addresses to be, and we separate out the read address and write address and all this stuff, right? Here in this model, it was still somewhat little simplified. It has one single address line, separated data line. But now in the register file, we have like two read address, one write address, one data in, two data out. Why we can do it? We can do it because we have abundance of space. We can add many lines as we want. And secondly, it will serve the purpose. If you recall the previous session before the break, when we talked about this, how an A plus B, C equals A plus B actually executes. Remember at that addition operation step, that instruction, controller need to fetch two register value at the same time. So only with this kind of hardware structure, we should be able to do that. We can parallelly read two register. We can send out two address separately and take them, read the data out from the register file at the same time. Otherwise, with the other model, simplified model, controller need to do two cycle of read operation to fetch two data, and that will slow down the processor. Whereas making more parallelized connection in this process. And we'll see, later we'll see in CS147, towards the middle of that course, we'll see the necessity of the parallel write there. It is something to do with the pipelining structure. I'm just giving a sneak peek. Once you go there, you will understand why write also need to have a separate address and separate data in for the operation. But for time being in this course, assume it is also to improve the efficiency and performance of the processor. Okay, so we start from a memory model. We go into simplified register model. And from there, we evolved into a little more complicated register model, which serves the purpose of making a processor or execution of an instruction efficient. And we can do so because register file is a part of the processor and it is implemented on the silicon. We have abundance of space there compared to the motherboard. So that's the reason. The other distinct difference between register and memory, register usually has big space, means number of storage or amount of storage is very big, like 4 gig memory, 16 gig memory, something like that range. Whereas register file is very handful in number. The processor we'll be studying in this course will have only 32 register. 32 by 32 here means it's a 32 register and each of them is 32 bit. Okay, 32 register, each of them is 32 bit. So as a result, since there are only 32 register, number of address bit needs basically is log base 2 of 32, which is 5. So you see there are less number of address bits needed to access those register compared to the memory, whereas even 1K memory will have 10 address bits, where 32 needs just a 5 address bits. So that's the difference. Okay, any other question? Okay, it is 9:10. It is almost end of the class. I wanted to do some breakout session, but since we are running out of time, let's do it next day, the breakout sessions. Basically, I'm planning to give some hands-on problem so that initially first 5-10 minutes you discuss in a small group, try to come up with a solution. and then we come back in a bigger room and discuss possible solutions for the problem. Maybe next day I'll do it. So any question before we actually stop today's class?
Yeah, I had a quick follow-up question on a question that was asked earlier about the clock cycling and how it was 50-50 previously. And you said that it was less to conserve power. Is there any disadvantages to having a shorter clock cycle?
Definitely the circuit get complicated, and controlling those things is getting complicated. So there is a trade-off between, like, otherwise people will do infinitely, making it like shorter positive cycle, right? But there is definitely other consequences comes up. Those are more like an electrical engineering area discussion, but it will complicate the circuit.
I did have a question about late enrollment.
Yes.
Oh, so I guess I just wanted to add this class, but I wasn't here on Monday. So this is the first time I'm showing up.
So you have the Canvas access, right? And you are registered in the Zoom. Definitely you have a Canvas access. Please send me an email. Okay.
Okay,
I think are we in touch with each other through the email?
No, I
Okay,
just
so you-
decided to join.
Okay. Maybe, yeah, I usually look at the class list about maybe Friday or Saturday. And if I see there are new enrollment, I usually communicate with them. There are certain steps we need to follow up there, and we'll go from there. But nonetheless, send me an email also upfront, okay?
Okay,
So go to the, so you cannot see the announcement section, right?
no.
Okay. So just send me an email with your name, ID, just as a subject line, do a late registration request. So there is a YouTube channel. Do you have the link through the
Yeah,
Canvas?
someone
Right?
gave me that.
Yeah, so there is an specific video about late registration student. You might want to watch that first.
Okay,
Okay.
yes.
All right, so let me stop the live streaming.